All right, back in the barn. We are going to finish off chapter 6 today. We're moving right along, and we're going to look at applications. So we're going to look at applications of the exponential function and then also the log function. And if you're looked at the page on Canvas, you noticed that I wrote down a bunch of word problems. So I wrote them down there so I wouldn't have to take the time to write them down on the board. So you can pause it or write them down yourself or print them out, whatever you want to do. But just to kind of save some time, I won't have to write the whole problem on the board, but we'll go in the order. I have them written right here, and we'll go in the order that I wrote them on Canvas, okay? Just to make our life easier. So when it comes to applications for the exponential or the log functions, the first one that we see would be looking at compound interest. So remember that when we graphed this, we saw that we had either a growth curve or a decay curve. And so we want, like in case of money, we want our money to grow. If you put it in the bank or you put it into a savings bond or whatever you put it into, the hope is that the money continues to grow. And that's called compound interest. Now there are two types of compound interest. The first type is just regular compound interest, so what we've got here. And the formula for compound interest looks like this. A equals P times 1 plus R over N to the NT power. So not the prettiest formula, but it's not too bad. When we're doing this, the P is going to stand for principal. So how much money did you put in the account? 1 is the number 1. R stands for the rate, but make sure that this is in decimal form, not percent form, so decimal. Now N is the new guy. N stands for the number of compounds per year. So with compound interest, what happens is you give, let's say a bank, you put money into a savings account. And most savings accounts compound monthly, which means at the end of the month, the bank gives you an interest payment. Cha-ching! And I think like my interest payment seriously is like 7 cents. It's really an embarrassment, okay? Then the next month comes along and I get another cha-ching. And so I get compounded 12 times a year, every month. Okay, you could be compounded weekly. You could be compounded daily. If you're compounded daily, at the end of each day, you get a little cha-ching. Tomorrow you get a cha-ching. So there would be 365 cha-chings through the whole entire year. So N is gonna stand for that, how many cha-chings you get. And so what's happening is every time you get that cha-ching, your account has grown a little bit. So if it's monthly, at the end of the month, you get, as long as you haven't spent a ton of money, if it's in the savings account, you get a little cha-ching, your money grows. Then at the end of the next month, cha-ching, and your money grows a little bit more. Now, if you're investing, hundreds of thousands or millions, that cha-ching is really nice. If you're like most of us, the cha-ching is like, why am I wasting my time? But that's the way this works. So N is going to be the number of compounds per year. And here, T is going to be time, and it's also going to be in years. Okay. So let's say we're doing number 1 now, and it says, how much money will you have in 5 years? So we'll say number 1, in 5 years, if $8,000 is compound or is invested at 6.5% compounded weekly. Okay, so that's what you have in that first problem on the Canvas page. Okay, so it says that it's compounded weekly, which puts us into this formula. That's the part, compounded weekly. So we just need to plug in the pieces and then plug it into our calculator. So we're going to say A, which stands for the amount, how much you have, is P, which in our case is the 8,000, times 1 plus R over N. Now our rate is 6.5%, but we're gonna write it as 0.065. And we're gonna divide by the number of compounds. So if it's compounding weekly, that's gonna be 52, right? 52 weeks in a year. And then it says to raise this to the NT power. So we're gonna go 52 again, and it said we're gonna be in that for 5 years. So we are going to see what happens. Now, the easiest way to plug this into your calculator is all at one time with the parentheses that are written there. So we start with 8,000, parenthesis 1 plus 0.065 divided by 52, close parenthesis, caret, parenthesis 52 times 5, close parenthesis. And I got 11,069 and, oh, look at that. It actually goes 0.998. So that thing would round us actually up to 11,070. And then hit it with a dollar sign. Okay. So we've got $11,070 if we leave our money in there for 5 years. So it has grown quite a bit, but you gotta leave your money there. And you have to have the $8,000 to invest in the first place. Okay, so like I said, most bank accounts compound monthly. This one would be a nice one if you could find someone that would compound weekly, that would be great. But there's the best, and that's what we wanna look at next. It's also compounding, but it's a little bit different here. So let's get the board erased again. And this time we're going to look at compound continuous. And what compound continuous means, continuously compounding, means that your money grows all the time. It's in there and it's growing 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 and it's growing. You don't have to wait till the end of the week or the end of the day or the end of the month. It's always growing. So that's ideal. You want it to be always, always growing. And thinking about exponentials, when it comes to the ideal growth rate, what you're looking at is P times E to the RT power. The formula changes, and instead of just using random numbers in here that go with the problem, all of a sudden the E comes into play. And remember that E is that perfect growth rate. So if it's good for animals and population and all of that, it's good for your money too. So this is what we're hoping for. So then number 2 here, sorry, the trash man just showed up and the dogs are like, oh, I want to bark at the trash man. Okay, so number 2 is asking us, it says, what if we were able to find a bank that would compound continuously? So we were looking around and we found that, but then we find another bank and they said, yeah, we'll compound you continuously. Now, how much money will you have if we choose this option? So now all of a sudden the compounding weekly disappears. We don't need that anymore, but all the rest of the information stays the same. So we go A equals, P is still our $8,000. Then we go E, our rate, RT, so 0.065, times our time, which was 5. Now, when you do this in your calculator, the calculator is going to give you the first parenthesis, and we just need to close it. Okay, so if you haven't done E on your calculator before, whether you're using the big guy or the little guy, okay, your E is going to be on the left-hand column here, and wherever your LN is, the E is right above it. So we go 8,000, and we go second E. And notice that it gives you that parenthesis. Then we go 0.065 times 5 and close it. Okay, now, as you look at the answer there, it's not like it's a huge big difference, but that's because we only started with 8,000. If we started with $8 million, the continuous would really be a difference. So I got $11,072.25. So if we're able to get it into a continuously compounding account, we can make an extra $2.25 in 5 years. Okay, so like I said, not great, but it's better, and it's what you're going for. Okay. Okay, yeah, we're having just major dog barking. I apologize for that. All right, so compound interest and compound continuous interest, those, especially if you're going to business calc, those guys you need to have like down. PERT, everybody should know PERT, okay? Everybody should know PERT. So then the next type of problems that we're gonna work into are, oh wait a minute, we decided that didn't work. Are growth and decay. And obviously we've just been doing growth of our money, but we're gonna look at growth a little bit more, and then we're gonna also look at the decay. Now, depending on where you learned growth or decay, if you've learned this before, you might have seen different letters. If you learned this from a different book, and when you go to calculus and you learn this, you might see it. So what I want to make very clear to you is that the letters in the formula don't matter. It's the formula that matters. So when we look at growth and decay, or decay, it just, like I said, it really doesn't matter. We can use n, and n is going to equal n sub 0 e to the kt power. Okay, n equals n sub 0 e to the kt power. So for whatever reason, when we turn this formula into just growth or decay, we start to see just differences here. So instead of a P being here, instead of it being PERT, it's NECT, okay? But the N stands for the N sub 0 stands for our original amount. So this is still like your principal, so that's your original or your starting. And for whatever reason, they decided to let K equal your rate. So instead of R, they're using K. Now, as I said, it's common to see different letters in here. So one other common one is A equals A sub 0 E, oops, not dry apparently. Let me try again. So, different pen. So A equals A sub 0 E to the kt power. All right, N, it doesn't matter. It doesn't matter if you like C, I guess you could use C. But anyway, it's common to see these two letters. Just depends on who your teacher is and who's teaching you. But pretty much always the K will be there, standing for the rate. Okay, so let's look at number 3 then that we've got there. And number 3 is talking about bacteria. So it says, if 200 bacterium are placed in a petri dish at the beginning of an experiment. So we know that we've got 200 originals. So that would be the N sub 0. They have a growth rate of 4.8% per hour. So their K is 4.8%. But what's important here is to notice that this is in hours. It's not in years like we're talking about our money. Then it says how many bacterium will be present at the end of a day. How many at end of day? they're mixing you up a little bit here. If the growth rate is in hours, everything else has to change to hours, okay? So even though they said end of the day, we're gonna change that into hours, so we're actually looking at 24 hours. Okay, so when you're dealing with the bank, it's always yearly, but here we gotta be very aware that they're gonna mix it up a little bit on us. Okay, so again, whichever one you like better, but we're gonna say the number at the end of our experiment is gonna be the original times E, and then we're gonna go to the K, the rate, but remember 0.048, and we're gonna look for 24 hours. So again, remember the calculator is gonna give you that, just close that little parenthesis on there, and let's see how many bacteria we have. 200, second e to the x, 0.048 times 24. So I get that there should be 630, nope, wait a minute, 632.9 bacteria. So this is how a science experiment is done. If you know that if the bacteria are just allowed to grow, that if you put 200 in there, at the end of the day, there should be 632.9. Well, let's say you were to pour some Lysol in your little Petri dish. That's gonna change this ending number. So maybe it's not 200, maybe it's gone down and it's only 91. And you know that it should be 632, so you go, wow, that Lysol is really killing off the bacteria. So that, I mean, obviously there's a bit more to it, but that's my basic science experiment, okay? Alrighty. So again, using our same formula, same format, just with different notation. Okay, so I'm gonna figure out what the barking is all about. We'll come back and do the last couple examples there.